Today, we're going to put on our detective hats and follow the clues with a true scientific mastermind, J Thomson, as he cracks one of the biggest mysteries in the history of physics: what an atom really is.
I mean, think about it. That was the huge problem facing scientists back in the late 1800s. They were trying to understand the very fabric of reality, but the main suspect was, well, completely invisible. The only thing they had to go on were the strange effects it left behind.
Now, to really get why Thomson's work was so earth-shattering, you gotta understand what everyone believed at the time. For literally centuries, the foundation of all science was built on one simple idea: the atom.
And that name says it all. The atom was it, the end of the line, the fundamental, uncuttable thing that everything in the universe was made of. To even suggest it could be broken down into smaller pieces, that was like challenging 2,000 years of absolute scientific certainty.
So the first real crack in that ancient idea came from this bizarre thing happening in vacuum tubes. Scientists found that when you zapped electricity through them, this mysterious beam would just appear, making the glass at the end glow. They called them cathode rays, and nobody, and I mean nobody, could agree on what they were.
The entire scientific community was basically split into two camps. On one side, you had people saying these rays were some kind of wave, kind of like light, moving through this invisible stuff they called the ether. But the other side argued, no, these are actual physical bits of matter, tiny particles that carry a negative charge. This was the mystery that J Thomson decided he was going to solve.
And this is where our detective enters the story. Thomson didn't just look at the problem like a physicist, he approached it like a master investigator. He set up a series of brilliant experiments designed to force these cathode rays to give up their secrets.
He had this awesome, logical three-step takedown. First, he had to figure out if the negative charge was just some weird side effect or if it was the ray itself. Second, he had to pull off something no one else could. He had to bend the ray using an electric field. And third, if they were particles, he had to figure out, what are they like? How big are they? So for that first step, he built this special cathode ray tube with a charge measuring device, an electrometer, kind of off to the side. And guess what? It only picked up a charge when he used a magnet to bend the ray and aim it right at the detector. The conclusion was totally inescapable. The ray was the charge. They were one and the same.
Now here's what's so cool. Other very smart people had tried to do this and failed, but Thomson had a hunch. He suspected their vacuum tubes just weren't empty enough. So he built a tube with a way better vacuum and voila! He was able to use electric plates to bend the beam, proving without a doubt that it was made of negatively charged particles.
And here it is, the smoking gun. In his own words from 1897, the evidence was just overwhelming. He had cracked the case. Cathode rays were not some mysterious wave, they were real particles of matter. Okay, but this next part is where the discovery went from being really important to being absolutely world-changing. By carefully measuring how much the ray bent in both magnetic and electric fields, Thomson could figure out its mass-to-charge ratio. And the result was just stunning. These new particles were more than 1,000 times lighter than a hydrogen atom, which, up until then, was the smallest thing anyone had ever known.
Thomson initially called these brand new, tiny particles corpuscles, and because he got the exact same result, no matter what gas he put in the tube or what metal he used for the cathodes, he made a huge leap. These corpuscles had to be a universal building block of all matter. We, of course, know them today by the name that stuck: electrons. But you see, solving one mystery just created a brand new one. If these tiny negative electrons were inside atoms, but atoms themselves were electrically neutral, what in the world did an atom actually look like? The old indivisible solid ball model was officially toast.
So this led Thomson to come up with his famous plum pudding model in 1904. Just picture it. He imagined the atom was this big ball of positively charged pudding, and scattered throughout it were the negatively charged electrons, like little plums. These electrons were orbiting around inside, and the whole thing was perfectly balanced to be electrically neutral.
Now, spoiler alert, the plum pudding model didn't last forever. In fact, it was eventually replaced by a new model developed by one of his own students, Ernest Rutherford. But that doesn't matter. Thomson's discovery of the electron had kicked the door to the subatomic world wide open, and his influence was just getting started. I mean, the hits just kept on coming. He snagged the Nobel Prize in 1906, obviously, but then in 1912, while studying positive ions, he noticed that not all atoms of neon were identical. Bam! He just found the first evidence for isotopes. And the method he used to do it? It became the foundation for a technique we still use all the time:
mass spectrometry. But for all his personal discoveries, this number right here might be his most incredible legacy: 7. Thomson wasn't just a genius in the lab, he was an unbelievable teacher and mentor. 7 of his own students and research assistants went on to win Nobel Prizes themselves.
And look at this list. It's not just anybody. It's a who's who of 20th century physics. We're talking Rutherford, who found the atomic nucleus; Niels Bohr, who gave us the model of the atom we learn in school; Max Born, one of the founders of quantum mechanics. The man basically built the next generation of physics superstars.
And you gotta love this. In a perfect, almost poetic twist, J Thomson's own son George won his own Nobel Prize in 1937. And get this, he won it for proving that the electron, the exact same thing his father discovered as a particle, could also act like a wave. Just an amazing little piece of science history right there.
Okay, so we've followed the clues, we've cracked the case, we've looked at the incredible legacy. What's the bottom line here? What's the big takeaway from this whole detective story?
Well, it's this. Finding the electron was so much more than just finding a new particle. It was a moment that completely shattered 2,000 years of scientific bedrock. It proved the uncuttable atom could, in fact, be cut. It opened up the door to the entire subatomic world and kicked off the revolution that led directly to quantum mechanics and everything that came with it. Thomson's story is just this incredible reminder that even the things we are most certain about in science, our most deeply held truths, are always up for debate. He took a concept that had stood for millennia and just blew it wide open. It really makes you wonder, doesn't it? What indivisible idea that we hold today is just waiting for the next J Thomson to come along and prove us wrong?